That was gonna be light. Really good. I got mugged.
Too bad there were no witnesses.
Bro, you witnessed it.
I didn't see it.
Shut up.
I just heard someone say I got mugged. You don't want us in the front? Is that a yes or no? Speak English.
Okay.
Okay, let's go.
Okay.
Okay, so let's grab this one.
Okay. Just sit here. Or you good? Okay, fine. You can sit with,
I have to make sure he's paying attention.
Okay,
you can sit with the nickel mugger.
okay, let's start. So it's on air now. Be careful about your words.
Okay. I'm getting confused. Just kidding.
Let's
I got
grab
mugged.
this one. From AP, from page 242.
Yeah, pencil.
242. This is AP Physics B. Basically, today we'll talk about. So last time we talked about the charge. We talked about the E field. We talked about potential, and we talked about the energy. Okay. Today we'll again start with charge, but we will talk about the movement of the charge, storage of the charge. So we'll start with a capacitor, storage of charge, and then talk about movement, means the current, and then we will talk about the resistance and something else. Okay, so let's start at page 242. The first thing what we talked about here is not here, but from last week.
Still here. That's right.
Okay, at a certain amount of time, with certain current, that's how many charge we move to some object. Okay, so in term unit, this is coulomb, this is current, which is ampere, and then time, of course, is second. Okay, so 1 second with 1 ampere, you will move 1 coulomb of the charge onto some object. Okay, that's the starting point. And then on the figure 16.3, that's normally what we use to draw the circuit. We have wire, we have resistance, we have, we have the battery. The battery normally we use 2 of them. One is means positive, one means negative. Okay, the positive voltage and the negative. Oh, there's a handout, 2 of them. And then there's a switch. The switch normally what we draw is that we draw this way, means at time 0 we close it, or sometimes we draw the other way, means at time 0 we open it. Okay. Other than the battery, there are something called ground. Normally ground we draw more than 1 negative. We draw 2 or 3 or whatever. Means that this one, the voltage is equal to 0. Okay? That's a circuit. What else? A lot of time we draw the bulb. So by across means the light. Okay, it will light up. Normally we draw the voltage. So here means it's a voltage meter. Okay? And if we draw a circle with ampere, means ampere meter. Basically this one will measure the current go through it. This voltage meter measures the voltage across it. The property of the ampere meter is that the resistance of this ampere meter is equal to 0. Okay? Means no voltage difference between the 2 sides of the ampere meter. Basically you can ignore it. The current just goes through. But by go through it, you will read what kind of current goes through it. On the other side, the voltage meter, the resistance is infinite. Means this voltage meter does read the voltage difference between these 2 points without taking any current go through it. So the current just go through the resistor at the beginning. Okay. So what you saw here, the ampere meter and the voltage meter, they introduce into the circuit without disturb the circuit at the beginning. Okay, the ideal case. Of course, sometimes we will see this one will in parallel with about 100 kilo ohm or 1 mega ohm, so a big resistance, so some current will go through it. Okay, we'll talk about this more later. Again, this is on page 242. We just talk about this one. We just talk about all the symbols for the circuit. Okay, next page we start talk about resistance. Here we have the first equation means that at certain time with certain current we will move certain charge. Next thing is that if we pass a certain of the current go through this resistance, the certain amount of current, there will be a voltage drop. There will be a voltage drop across this resistance. So normally we use this one, V equal to IR, means that the voltage drop will be larger if your current get larger, or your resistance is get larger. Okay? If you use a plot, this is a voltage versus current, and you have a slope. Okay? Means if your current is higher, the voltage is higher, and this slope, how slope, what's the steep? If it's flat or steep, depend on this resistance. The slope is the resistance. What you will see is that all the resistance means a straight line and pass the 0 point on this V versus I plot. There are certain things doesn't behave like this. For example, there are certain things behave like this. This is called diode. A PN junction, we don't need to use this in the exam or whatever. The PN junction with a diode means that at one dimension, when you apply the voltage, the current will go up, just kind of like resistance. However, on the other direction, no matter how much of negative voltage you put on, there is no current. So it means the current just goes through one direction without going the other direction. So what you saw the symbol will look like this. The current only go this direction, but not go this direction. Okay? But for a single resistance, what's happening is that it's just a single line and pass the 0 point of this VI curve. Okay? Now, the next equation, the R equal to rho times L over A. We'll talk more again later. This is a physical understanding, microscopic physical understanding of why there is such resistance. Okay? Think about a wire. This is, let's say, is a copper wire. Okay? What's the resistance goes through it? If we get the current go through it, there are definitely some voltage V1 and V2. There will be a voltage difference between V1 and V2, and then due to a certain current, which is current times R. So the question is, what's R related to this kind of copper wire? Okay? What we know is that if the wire gets longer, means there's more resistance, and this R can be larger, or the same current, the delta V will be a little bit larger. Okay? So first thing is that this resistance will be proportional to L. Means the longer of this copper wire, the longer of the larger of the resistance. Okay? Second thing, it's proportional to inverse of area. A is area. Means if I get the wire a little bit larger, what's happening is that the electron can go through here, can go through here, instead of all the electron go through here. So the pipe is bigger and easier for the electron to go through it. Okay? So it's inverse proportional to the area. The larger of the cross section, the lower in terms of resistance. The third one is rho. Rho is called resistivity. It's a property of the material. If you flip the page, on page 045, there is a resistivity for different materials. What you can see here, everything is quite small number, 10 to the minus 8, other than carbon, 10 to the minus 5. So means rho is very small, 10 to the minus 8, means R is small, means that you can pass through a high current, like 100 amp of current, with this kind of very small resistance, and the voltage drop is really small. That's what we use at home. At home, our power supply normally is 110 watts. However, the ampere normally we use is 100 amp. That means the resistance on the metal wire is much less than 1 ohm. If it's 1 ohm times 100 amp, it will be 100 watts. So the voltage go to your appliance is only 10 watts, right? So basically, the wire is so big that cross section is so big that this one is only 0.01 ohm. Okay, so the voltage drop may be only 1 watt. In that case, in order to achieve this 0.01 ohm, what we need is the distance cannot change. The house is that big. Either we need a wider, bigger wire, and also we need to use some material that the resistivity rho is smaller. The smaller the better. So what you saw here is that the copper is pretty good. That's what we normally use for the conductor. There are certain things not that good, like tungsten. Okay. Here, let's do some guess. Let me erase part of it. What we talk here is 10 to the minus 8 in terms of resistivity, ohm meter, that's the unit. That's for the metal or conductor. How do you think about the insulator? For example, how do you think about the air? What do you think the air should be look like? 10 to the positive 1? 10?
Way bigger. But
I don't know what that
like
means.
16. Okay. So that's how much in terms of difference in terms of material. It's so many difference in terms of resistivity. Is there a number you can get from these two? 10 to the 24, right? Does it mean anything to you? Think about how many atoms per cubic centimeter. 10 to the 23, right? Each atom may contribute 1 or 2 or 3 electrons, something like that. I didn't mean that you should count by electrons to calculate the resistivity, but on the other side, what I want to say is that how many atoms in the air and how many atoms in the solid, and that will kind of limit how many electrons it can provide. Okay, in the air, the density is so low so that not many electron there, atoms there and electron there. Okay, so just to give you a big difference. And how do you think about the water? Water is a conductor or insulator. Water depends on what's happening in that water. If you have some ions, for example, you put some salt, okay, into the water, there's sodium ions or whatever, then it will be conducting. If someone really process the water, make sure there's no ions in that water, the water is a very good insulator. Okay, but normally the water that with ions, with a little bit salt or whatever, is 10 to the minus 1. Okay, so in between of these two, and there are some other things. Glass is 10 to the minus 10 to the positive 10, and a bunch of other things. Okay, let's look at the sample problem. The sample problem talk about the copper wire. Just have a quick read. I erase that one. So it's a very simple one, just use the equation we got. Okay, this is super easy, right? So basically, it's talk about the wire, the resistivity 10 to the minus 8, the length 1.2, and the area. The area is in terms of meter square, so it's 10 to the minus 8. Okay. So it's 170 ohm. Meter square. What's the cross section of this one in terms of millimeter? Make sense? Means what? Means is about 100 micron by 100 micron. What thing is have this kind of cross section?
Hair.
Your hair. Okay. 100 micron is in diameter is about your hair. Of course, someone is thicker, someone is thinner, but it's a copper with this kind of diameter. You have about this kind of ohm in 1 meter. So that's why our copper wire we use at home is much thicker. Bigger in cross section than this, right? We just need to get 10 times bigger in one dimension. So it means that 1 millimeter by 1 millimeter. Then the resistance will cut by 100 times 1.7, right? And 1 millimeter is not big deal. Normal wire is even wider than that, bigger than that, right? So that's okay. Okay, let's keep going. Yeah, ohm load 10 watts battery, so just 10 over 1.7 or 1. So you have the ampere. Okay. Electrical power and energy. The final equation is like this, but I want to ask why we have this kind of definition. Of course, this is voltage, this is current, and this is the power. And if you talk about internal unit, the voltage is watt, current is ampere, and power is what? Watt. Right? So why we need this? Remember when we talk about the voltage, why we define the voltage energy, electrical potential? Why we define this one? When we define the voltage, we are talking about the power. We said that if we have a certain amount of charge move from infinity away, move to a certain position which have a potential V, we need to put this amount of work onto it. Okay? So that's work over the charge is the power. That's at the very beginning what we define. Okay? So that means this voltage is what? This is Coulomb, this is Joule, right? How many joules? So this voltage is equal to what? Equal to Joule over Coulomb. How about ampere? Ampere is how many charge goes through a certain time, right? So ampere is how many charge goes through a certain time, second. So if we multiply these two, it's joule per second, which is what? Okay. So this is from very beginning when we start to define the potential, electrical potential. We want to talk about the energy to move a certain charge. That's why we define the potential. And suddenly we found that by multiply this voltage potential with certain current, we again get the power. Okay? Because this current is how many charge we are moving, just like the charge here. Okay? So just I will finish the loop, self-consistent. Okay, instead of the power equal to voltage times the current, if we put this one, V times I into it, it will also equal to V square over R and I square times R. Make sense? Voltage is equal to IR, so IR times I is I square R. But on the other side, you can put I here, so V over R, so V square over R. Okay? So there's many ways to calculate the power. If you calculate the power from a battery, what's the best way to do it? You just calculate the voltage across the battery and the current. Okay? If you calculate the power goes through a lamp or goes through a resistor, if you know the current, you use this one. okay? Because you know the resistance. Or if you know the voltage, you can use this one. Okay, quick example. This means how much energy is used by 10 ohm for 24 over 30 minutes. Okay, how about the power first? The power is, we know the resistance and we know the voltage, so V square over R. Make sense? So 24 square over 10 ohm, something like that. Next, about the time. In terms of total energy, the total energy will be power times time. The time is what? Is 30 minutes, 30 by 60 seconds. Okay, that's how much. And finally, it got 18k joule. Okay. The reason I give you this derivation is that I want to introduce another unit that's not discussed here. It's called kilowatt hour. Okay, that's normally what we use at home, right? We pay the electricity by kilowatt hour. What's the price for 1 kilowatt hour? We pay 10 cents. Okay, I mean depend. Normally it's about 15 cents or something like that, but I just say 10 cents for easy calculation. Okay, means what? 10 cents is not a big deal. Means 1 kilowatt hour. Of course, we should save energy. Okay, but it's not big energy. Okay, it's just 10 cents worth energy. How about this? This is kilojoule. What's the relationship between them? So 1 kilowatt hour is equal to what? 1,000 watt times 1 hour, right? 1 hour is 3,600. 3,600 seconds. This is what? This is 3.6 kilojoule. So this one, you just burn something like 18 kilojoule. There are other, if I do this one, so about 200 times bigger. This one is what? Is a 10 ohm resistor, 24, let me do a quick calculation here. 24 square is what? Something like that? I don't know. Tell me wrong, but roughly that. This means what? Means a 60 watt lamp. You open a 60 watt lamp for 30 minutes and you burn 200 of the 1 kilowatt hour, which is 10 cents. Okay? Means you burn really few, but you should turn off all the lamp again, okay? But just want to know, just by lamp itself, it doesn't kill a lot of energy. So in your home, what kill energy? Heating, yeah. Heating or cooling. So air condition or heater. Heater mostly gas, but the air condition definitely kill a lot of energy. We will talk about that maybe later, talk about some, but just for the lamp, it doesn't take a lot. However, it take, every day you need to use it. So what's the, people call it what? The energy cost for the illumination. So what's the total energy percentage worldwide in terms of how many energy we generate will be spent on this kind of lighting? Do you have a percentage guess? Guess in percentage? 1? 20%. Why is that? Because around the earth, a lot of people, they have energy used only for lighting. They don't have energy for air conditioning. They don't have energy conditioning. They just want to light and study or whatever. But yeah, that's the truth. 20% of the energy is cost in lighting. Yeah, although it doesn't, really not much for us. Okay, let's keep going. Series and parallel in circuit. So if you have resistance in series, and then you have resistance in parallel. I didn't list all there, but it's like R1 plus R2 equals R total if it's in series. In parallel, it's R1, 1 over R1, 1 over R2 equal to R. Okay? Why is that? What's the definition of resistance? Voltage over current. Make sense? Okay, let's do the derivation. First, let's have two resistance in series. There's R1, there's R2. So it means that there's V1, there's V2. Here and here, here and here, right? The current will be the same. Make sense? It's a series. So how many charge move into this? How many charge will move out of this, and move in this, and move out of this? All of them at the same amount of time is the same. Okay? Current is the same. Continuous. So R is equal to V over R. V over I. The voltage is equal to this one plus this one. Make sense? V1 over I is what? This is R1, right? And this is R2. Okay? So that's in series. How about in parallel? R1, R2. This time the voltage is the same, right? Because it's a single metal wire from here to here. So the voltage here and the voltage here, they are same, fixed. However, there's Y1 and there's I2. And there's I total, which is the sum of these two, right? If there are two charges come in, one go this way, one go this way, or something like that. Okay? Again, let's calculate R. R is equal to what? V over I. I is what? I1 plus I2. Make sense? Let's do it again. So it's equal to I1 over V plus I2 over V. Make sense? I just divided V to the bottom. V over I1 is R1, right? But it is flipped. So it's equal to 1 over R1 and 1 over R2. Okay? This is R. So if I put this one into here, it will get this equation. Make sense? Okay. Let's look at the sample problem on page 215. Have a look. Okay, there are 20 watts from 8 ohm. Determine the current and the voltage across each of them. Watts. Okay, first these two are parallel each other, right? So this one is on this. Normally when I do this calculation, I use this. R is equal to R1 multiplied R2, R1 plus R2. Okay, you just do the derivation, you will get exactly the same thing. And in Chinese, I always remember this as 上乘下加 means on the top is multiply and in the bottom is plus. But I don't know, I mean English better for you, so think about one way to remember that. Okay, multiply on the top, sum on the bottom. Take much longer. 上乘下加 is much shorter. No, so okay, anyway, and when you make this kind of cheat sheet, your teacher cannot understand it. Just kidding, don't worry. Okay, just try to remember it. So top is multiply, 4 by 4. Bottom is what? Plus 4 minus 4. This is equal to 2. But on the other side, I know that if they are the same, in parallel, they just cut to half. Okay? There are certain things you can remember. So just 2 ohm. The voltage will have same current go through this 2 ohm and 8 ohm. So the voltage will be separate by this one and this one proportional to their resistance. So 20 watts will separate 4 watts here and then 16 watts here. Make sense? if it's forward here, I don't care about total current. I just calculate this current directly. It's 1 amp and 1 amp because it's 4 watt over 4 ohm. Here is 2 amp because 1 amp adapt to 2 ohm. You use the other. So voltage drop and current. Too easy for you, right? Okay, let's keep going. Capacitor in series and in parallel. So this time is a little bit about the capacitor. How about the fundamental equation definition of capacitor? Yes, means that in order to put certain amount of charge onto an object, okay, you need to increase the voltage, the potential of that object a little bit, and the coefficient is so-called capacitor. For example, I have a metal sphere. I just put some plus charge onto it, and compared to the infinite long, there will be a potential, okay? And then V times C is equal to Q. Q is the thing I've been. C is the capacitor of this one compared to ground or compared to a infinity away vacuum. What's the capacitor look like? Or if you do this kind of capacitor, you'll have plus here, negative here. How many charge here? How many charge here? They are same, negative Q and positive Q. So Q is equal to CV. V is voltage occurs here. C is belong to this device. Okay. Now let's talk about the series and the in parallel. Let's talk about in series. Okay, I don't care about the battery. Again, same thing. When we talk about series, we always talk about the voltage adapt, right? So there's V1, V2. C is equal to what? Q over V, right? V is equal to what? V1 and V2. Okay? Next question. Right now I say there is a charge of Q, means that if I consider this as a single capacitor, one side is positive Q, one side is negative Q. Okay? My question is that how many charge here, how many charge here, charge here, charge here? What you find is that this is positive Q, this is negative Q. This is positive Q and this is negative Q. Okay? So just like this, the positive Q is here, negative Q is here. In the middle, what you found is that they are summed to 0. Okay? Or on the other way, since this is capacitor, no current really flow through it. The only thing changed is that the charge neutral capacitor will have some positive charge go this way or negative charge go this way, so that they just split, redistribute the electrons, but nothing more, nothing introduced into the middle part. Okay? So what we know is that same as this Q, the Q is around this capacitor. Okay, so what I can do is next 1 over V1 over Q1, Q, plus V2 over Q. This is equal to 1 over, this one is 1 over C1 and 1 over C2. So 1 over C is C1 plus C2. Okay? Very similar thing you can derive for the parallel case. But in terms of parallel case, what we have is that the same amount of voltage here will introduce Q1 plus Q1 negative Q1 and plus Q2 and negative Q2. Okay? So instead of C, Q over V, right now we really have Q1 plus Q2 over same amount of voltage difference across the capacitor. Okay? So this will be equal to C1 plus C2. Okay? So in terms of the capacitor, you'll have similar thing, just flip them. This one is in a parallel of resistance. However, this is same thing in terms of series of capacitor. This one is series in resistance, or parallel in capacitor. Okay.
Q is charge, C is capacitance. You can ask questions.
Okay, so let's go to page 252.
Yes.
That's the last section of this circuit. This is instead of talk about the resistance and then capacitor, we right now put one resistor and one capacitor together into same circuit. And what's happened is in the part C. So can you take a look when I erase the whiteboard? By the way, if I put this, means what? Means I got one battery, in series of second battery, so I can put it simple, or I can put 3 or 4. But it's same as this. I mean, I didn't tell you what's the voltage, so that's the same, no big difference. However, if I put this and then this, and I tell you each battery is 5 watts. So what's the voltage outside here? 0, right? One positive, one negative, because I flipped them. Okay. So this is a circuit. Instead of just series resistor or capacitor, we put one of them each. And at time equal to 0, I will switch, close the switch, so the current will start to move. Okay? Let me ask a few of things first. Let's talk about current first time. Maybe let's also talk about how many charge inside the capacitor. Okay? Before I turn off switch at t equal to 0 point, is there any charge on the capacitor? No? Right? So at the beginning the charge is 0. Okay. When charge is 0, what do you mean? What do you think about the voltage across the capacitor at time equal to 0? It's also 0, right? Because V is equal to Q over C. Q is equal to 0, so that let's say the charge Q in terms of, okay? If the voltage is 0 across this part, there's a certain voltage here, right? So what's the current here? V over R. Make sense? V over R. So at negative time, it's all 0, and suddenly it will jump to V over R in terms of current, as soon as you close the switch. Okay? This is similar thing. If I just have a battery with a resistance and then a switch, okay? When I close it, immediately you will find that the current will jump up. Make sense? As soon as I close the switch. Okay. So this means that the current, it can be a physical property that it can be changed suddenly. Okay. What other things that can be changed suddenly? If we have an object, we have the position x, right? We have velocity, we have acceleration, and we have acceleration of acceleration, doesn't matter. Is this one continuous or not continuous? This is continuous. However, the voltage, the velocity, you can suddenly change. If you want to suddenly change the velocity, what do you need to do?
Really high, like
Okay. Ft equal to mv, right? If you want sudden change this with a short of time, you need a really heat. You heat in order to suddenly change the velocity. Or otherwise, we can see it will gradually change if m is not equal to 0. Okay, give me certain things. How about A? it can easily suddenly change, right? A is F equal ma. So as soon as you apply the force onto it, it will have the change of the acceleration. So this one can be changed suddenly. This one, most of the case, you will change it continuous, unless you hit it really hard or the mass is 0, and the position will never change. You just change gradually over time. Okay. So here, what we say is that the current will suddenly jump to a certain high value V over R. Okay, let's think about at the end, the long time later, means that the current is keep going, and then finally this capacitor is fully charged, right? When it's fully charged, what's the voltage beside this capacitor? If this is V, here will be exactly same as V. Or the current I will go to 0 at the infinity of the time. The reason is that as long as the current is not 0, means they keep have charging to go into this capacitor. Q is equal to I delta T. If this one is not 0, I is not 0, then there will be keep amount of charge flow into the capacitor to charge it. Okay, so it's only finish the charging when the current is equal to 0. When the current is equal to 0, I times R, the voltage here, is equal to 0. Means that the capacitor has the same amount of voltage as the battery. Make sense? Okay, so that's at the end. At the end, the voltage will be equal to V. The charge will be fully charged to Q equal to C times V, right? And the current will go to 0. Okay, that's what we know about beginning point and end point. And in the middle, we can solve it. It's exponential exp or e to the x. Okay, we'll solve it later, but it will be an exponential decay, means it goes like this, or it goes like this, and you go like this. Okay, in this term, it's 1 minus exponential RC times over T minus something like that. Okay, but it will saturate at 1 times V. Okay, and start with if T is 0, this term will become to 0. So start with 0. And then for this one, it will be something like at T equal to 0 is just exponential TRC. So when it's infinite, it will go to 0. At the beginning, it will be equal to 1 times V over R. Okay? Don't worry about the coefficient. I will go through it again. It's the next level. But what I want to say is that it's important, to say the initial state, if it's jump, and then for the capacitor, voltage never jump. The charge in store never jump. However, the current will jump. And then what's the end state? End state, there is no current, means that the capacitor at the end will consider it as an open circuit. Because there is no current, so we can consider it as an open circuit. Okay? So voltage will be just equal to the battery, and the charge is fully charged. Okay, any question so far? So maybe let's get this one, the undergraduate textbook, page 589. Okay, 589. So we just go through everything about the capacitor, about the resistance, and about circuit. We'll go through it again with a little bit higher level understanding. Okay, again, first is capacitor is about charge. Everything about electricity is about charge. And from charge, we talk about the E field, we talk about potential, we talk about energy. And here we talk about the capacitor. So clearly on figure 26-2, what you saw there is that normally the capacitor have two things. And then on one of them you store some positive charge, and on the other you have negative charge. In between of them you have E field. When there's an E field, it means that there's voltage difference between these two objects. Okay, that gave us this equation that different voltage between the two objects will store some charge with this capacitor of C. Okay. Instead of in 26-2 the two whatever object, you can make a two plate in the next figure. That's a normal parallel plate capacitor build. So there is a voltage, a space of D, and then you can see that there is electric field in the figure B. Okay, there is electric field uniform vertically distributed across the center part of this metal plate. On the edge, there are some fringe effect. However, that's just a small part. Just mainly in the middle part, there's all the energy and the charge storage. Okay? Q equal to C times V. Okay, let's flip the page. So here we'll do some calculations. We'll do some calculation for two cases. One is parallel plate and one is a sphere. So first, let's do parallel plate. So what we have is two plates separated by distance of D, okay, with electric field in the middle, okay. There will be positive Q on the top and negative Q on the bottom. So the question is that what's the capacitor will look like, okay. So in order to calculate capacitor definition there is Q over V, right? Okay, what's the voltage? E times D, right? E is the E field, and what we know is E is uniform distributed inside. So from top to the bottom is always E times the distance of D. So E times D is the voltage. Sense? Okay, how about the electric field? If we think about the metal, this metal has positive Q. This positive Q will be put only at the bottom surface, and the other metal plate, the negative Q is only on the top surface. Okay? From Gauss's law, we can do a surface. This is how many charge inside, and this is the E field. The E field doesn't have here. The E is equal to 0 because it's inside the metal. There is no E field to go through this direction because it's uniform distributed and just surface normal, so there is no E field. Only E field is goes through here. Sense? Okay? And then what we know is that Q times, let me do this. This is total amount of charge Q. This is the E field times the area of A times epsilon 0. This is Gauss's law we learned last week, right? So this Q is set over A. So let me see. Okay, I just put the Q in. Q epsilon E over A. So the E field will be equal to Q over epsilon times C. With this two, we plug the E into here. What we have is C equal to Q D Q over epsilon A. It's equal to epsilon A over D. This is a capacitor for a parallel plate. Okay? Means what? Means this capacitor is larger or on the other side. C is equal to Q is equal to C times V. In order to have more charge, means that the same voltage, what we need is higher in capacitor. In order to have higher in capacitor, what we have is that capacitor is proportional to the area. Means that we just have a bigger capacitor, or we can parallel two capacitors. Okay? Even it's one capacitor, you can think it's a parallel of two. You can just cut half, and then you have somewhere outside. Okay? So first is that you get a larger in area. Second, it's proportional to 1/4 of D. Means if you get these two metal plates as close as possible, there's more chance you have store more charge. Okay? The E field is stronger and you have more charge into it. And also it's proportional to epsilon 0. Epsilon 0 is so-called permittivity. Yes, it's here on 26-10. It's a constant. This constant actually is directly related to speed of light. Speed of light is square root 1/epsilon 0 mu 0. One is electrical permittivity, one is magnetic permittivity. You don't need to understand this at this moment, but what I want to say is that epsilon is very in the air. It's a very good constant. It's just limited to some fundamental physics limitation like speed of light. Okay?
In the capacitor, the charges can move across the middle, right?
You mean move
Yeah.
around the metal, right?
Or like
No, it's air, right?
Okay.
So right now we're talking about epsilon, and it's air means that the charge cannot go to from one plate to the other plate. Only way it goes is from the outside circuit. Okay? Like what we have talked before. Whatever battery we have. We have positive Q, negative Q, positive Q, negative Q. For each of them you say it's a capacitor and it looks perfectly right. The important thing is here in the middle, it's sum to 0. The reason is that there's no charge move across the capacitor. Only thing is that it build up the E field. So the E field will attract some negative electrons or negative charge electrons to this plate, which will leave the other side positive. Okay? So it's only affected by the E field to the center part. No charge move around it. Okay? Yeah. So again, this is about how to build a capacitor. Okay, let's flip page 593. There is another capacitor we want to talk about is spherical capacitor. So take a look and I will just read this for the duration here. Okay, this is spherical capacitor. It means what? Original way to think about it is that I have a spherical metal with a radius of A, and then I have outshell with radius of B. So this is a metal, this is a metal. And then of course I can store something in the middle, let's say positive Q, and then some part on the outside, negative Q. Okay? I don't want to do this kind of fancy derivation. Let's assume B is equal to infinity. Means what? Means that if I just have a metal ball on an insulator post, and then I can store some positive charge onto this metal. So here is metal, here is, let's say, a glass, so it's in insulation, and I can always put some charge into it, right? It's a capacitor as well, but the capacitor, the other side, is the earth, it's the ground, which is far away from it, okay? And then there will be relative negative Q here to compensate. Okay. So basically, my question is that if I don't care about the B, what's the capacitor here? In order to calculate capacitor is equal to Q over V, right? Means that if I put positive Q of charge onto it, what's the potential on this metal? And then that's the capacitor. Compared to Earth, the ground. Okay? So what's the V look like? Oh, in this case it's A. Make sense? This in, the capacitor is equal to okay. Means that if I just have one metal ball here compared with the Earth from a capacitor, the capacitor is something like this. Doesn't matter about the distance here because this distance is much longer than the radius of A. Not like the other, the metal plate. This one is inverse proportional to 1 over D, the spacing. Here is too far away. So it's just a matter of the radius of A, which will build up the potential and the charge. Okay? Let's see how many things about the capacitor. Okay, let's do 2 examples and then we take break. Okay? So maybe one. So sample problem 26-2. Have a look. Three capacitors. And find the total capacitor. What does it look like for part A? One is 12, one is 5.3, one is 4.5. Okay, the first thing, the two capacitors, they are parallel to each other. What does it mean is? It's just plus, right? So it's like 17.3 for the top capacitor with 4.5 in the bottom. These two capacitors are in series, right? So what's the capacitor look like? Okay, multiply on the top sum and the bottom. And then you can do the duration is 3.57 microfarad. What's important about this kind of thing? I mean, just mathematically, the resistance in parallel or the capacitor in series doesn't matter. But if you have this kind of equation, what you got is that the result is smaller than both of them. The 17.4.5, the result is even smaller than the small capacitor. Okay, if you have 3 of them, 4 of them, it's always smaller than smallest. You can prove it from the mathematical. Okay. Part B, what's the potential difference? What's the charge on C1? V is 12.5 volts. Okay. How many charge? Q is equal to what? C times 3, right? This one is equal to something like 3.57 microfarad. So by multiply 3.57 with the 12 watts or 12 point something, 12.5 watts, you can get a charge. So that's a charge of 44.6 microcoulomb on this plate. Okay? Second, this one is coming from what? From two capacitors in series, right? Means in the top is positive Q, negative Q, positive Q, negative Q. So these two are equal to each other and sum to 0. So 44.6 on the top, on the bottom, on the top, on the bottom, all of them are 44.6. On here. The top one is in parallel of 2. The sum of them is 44.6. One of them is 12, one of them is 5.3, so 44.6. This is 5, and then times 12, something like this, I believe. So it's 31 microcoulomb. Okay? Or if you don't want to do this, you can use this charge to divide it by C to give you voltage. The voltage will apply to this capacitor, so you use CV again to get this kind of current. Okay? Okay, take a time to think about yourself. Let's have a break. Okay? Then we'll talk about more later. My book is much more expensive than that one. It's okay. You will spend yours.
And you're the other guy.
Yeah, the other guy, sure. My name is the other
And
guy.
who are you?
Huh?
What's your name?
Boreal?
Boreal? That's a weird name.
You said Boreal.
Okay, let's start.
You said Boreal.
Just can't remember if I recorded.
Boreal.
Okay, let's talk about energy density. Page 600.
Oh
Okay, so before we talk everything about the capacitor, but we didn't talk about the energy, or we didn't talk too much about the energy. So first, last time when we talk about energy is U is equal to 1/2 CV squared. 1/2 Q squared over C. Or 1/2 Q times V. Okay, it's all the same thing. But the main reason is that if we put the charge was the voltage, what we have is that Q is equal to C times V, means that it's following this single line. Okay? And what we know is that in terms of the energy, is we put one charge at a certain potential, electrical potential, we will have the work. So this one will come in, this one will come in, and then later this one will come in. So basically is the area under this triangle. That's why it's 1/2 Q times V equal to the total energy. Okay? So that's that. However, this is how we understand it in terms of charge. In terms of charge and in terms of the potential here. And and internal capacitor. The question is that if we have the capacitor and we have charge here, negative charge here, and we have E field, the energy is really stored in the charge or in the field. And turn out, actually the energy is stored in the field. Why is that? Think about one single charge. You put a single charge there, you start to put some voltage and some kind of charge so that you have some work. Okay? But actually it's because this charge will bring out some kind of E field, and that E field will expand in the whole area, and that kind of E field is where you store the energy into it. When you bring the second charge in, it will bring some actual E field, and these two together will build a new E field, and that's where you store the energy in. Okay? So in this one, what it shows you is that by use U is equal to the total over the area times the distance, means that the energy per unit volume. A is the area of the capacitor, D is the distance. So per unit volume, this is the total volume, this is total energy. The total energy per volume is the energy here inside 1 unit of volume. That's equal to what? CV squared over 2. This is the energy we have, and then over A times D. That's the energy density. And by derivation, if you use C equal to epsilon times A over D, so A and A will cancel each other, D will be there. So what you have is that this is equal to 1/2 epsilon V over D squared, or 1/2 epsilon E squared. Okay, equal to this. I don't try to ask you to remember this, but this is very important concept you need to build up through this moment. Okay, is that the energy is not stored in the in terms of charge, but really stored in terms of the electric field. It's E squared proportional to E squared with epsilon, depending on what material you put into the capacitor, and 1/2. That's something coefficient. Okay. Most likely you won't use it for your calculations, but instead you may use this one, the 1/2 CV squared to do the calculation. However, I just want to give you the concept that energy is stored in the E field between these two capacitors. That's where the E field is stored, the energy is stored, not just because of charge. Okay? So if you look at the sample problem, 26-4. So it's a sphere, radius 6.85 centimeter with some charge. Potential energy. So potential energy, we just use this kind of equation. It will be Q squared over C because we know how many charge. Okay, and we can calculate the capacitor just by 4 pi epsilon r. I didn't write it here, but we have derived that the capacitor is 4 pi epsilon r for a single sphere, or epsilon 0 A over D. That's for the parallel plate, right? Okay, so you plug this in and you can calculate what's the energy there. That's in part A. In part B, what's the energy density at the surface of the sphere? So the energy density is talking about the field. Okay, so what you saw there is that first you try to solve the E field. The E field is 4 pi epsilon Q over r squared. That's what we have before about the E field, and it use E squared and 1/2 epsilon E squared to calculate the energy. Energy is something there. Okay. Okay. I don't try to ask you to remember everything about the energy, but what I want to say is, E field to store the energy, but I want you to have this concept, the energy is stored in the field. Okay, let's flip the page. Page 613. This one we start to talk about the current. The current, of course, is equal to V over R, okay, the voltage over the resistance. But here, what we try to say is that the current definition is by how many amount of charge have been moved at a certain amount of time, delta t, okay? That's the definition of the current originally. And the other thing is that it will be continuous, means doesn't matter how much flow in, the flow out, I1 will be equal to I2 plus I3. Oh, on the other side, if I just say this is a naught, then the sigma of the current will be equal to 0 around a point, let's say P. For a single point P, the total current will be equal to 0. Means what? Means that no extra charge has been stored or extracted from this single point of P. Okay? Because it's a small point. It's a small point and nothing can be stored there. Okay? Make sense? So what you saw, the figure 27-3, the bottom one, doesn't matter how you turn your wires, it's always satisfied that I0 is equal to I1 plus I2. Okay, let's flip the page. What you say next is I is equal to V over R. Just the resistance. But this time on the figure on the left, it shows you how the E field goes inside that resistor. Inside the resistor, what you saw is that the current and then the E field. The E field just a parallel, so from one side to the other side, E times D will be the voltage drop. And the voltage drop will be equal to your current times your resistance. Okay? So immediately what you found is that the current and the E field, maybe there are some relationships since one side is free, the other side is voltage, right? With something related to resistance and something with let's say, the length here, okay? So if you follow the derivation there, let me see. On the back side, what you have is R is equal to rho Ls. Okay, that's the same thing we have derived. Depending on how long is the resistors, depending on inverse proportional, depending on the size, cross-section of the resistors, and of course the material. However, there's another important thing that you can try to remember is that this rho is equal to 1 over theta. So what we call the rho is the resistivity. And the theta we call it conductivity. Okay? The higher of the rho means the higher of your resistance. Okay? The resistivity means that the higher of the rho, the electron is harder to move through it. 1 over rho is theta means that the higher of the theta is more easier to have conduction, the conductivity. Okay? And the one important thing there will be J equal to sigma times E. J is current over area, means current density. The current over the area of the resistor, that's the current density. And the current density, it depends on the material. The material itself, the conductivity, which is 1 over rho, and then the E field. The E field is dependent on the voltage. The voltage is equal to the E field times B, let's say R, the length of the resistor. Okay? So these things will connect everything. However, Don't worry about this, don't worry about this, don't worry about this. It's not required in the AP physics, okay? But I just pointed out later if you pass F equal to MA, if you go to the semi-final, definitely all this is really important. So at that time, I won't talk anything about this side. I will start with here in terms of the advanced electricities. Okay. So on page 619, that's the resistivity bunch of things. What you can see there is the glass 10 to 10, the fused quartz 10 to 16, doesn't show the air. Okay, the metal is 10 to minus 8, and what important thing is silicon. It's called semiconductor. The silicon by different doping, if it's pure, you can say it's 10 to the 3, so it's quite insulator. The conductivity is quite poor. However, if you dope a lot of dopings, impurities, the conductivity can go, resistivity can be low, as low as 10 to the minus 4. So it's almost like a conductor. Okay? Depending on doping. Okay, that's about it. Let's flip the page. The power. The power in the circuit. The power in the circuit is equal to the voltage times the current. Okay? P is equal to IV. And we have to do the derivation. The voltage, the unit is joule per coulomb, and the ampere is coulomb per second. So at the end is joule per second, which is 1 watt. Okay? And also, since V is equal to IR, so you can have V squared over R or I squared R. That's the two explanations. That's simple. So if you look at the sample equation for an example, 27-6. So what you calculate the power here is that you know the voltage and you know the resistance, so don't try to calculate the current. Let's use V squared over R, and you can calculate the power 200 watts, and then you can do the derivation. That's what we're doing. Okay, let's flip. Now we have all the fundamental concepts about circuit. We need to talk about the circuit's derivation of the what's happening inside the circuit. The first thing actually in 28.3 is that sigma V is equal to 0 if it's a loop. Before we will talk about the sigma point P of I is equal to 0. Okay? So this is two equations. Okay? This means what? Means at a single point, the current in and the current out, the sum will be 0. In the first case. Second case, doesn't matter what I have. If I calculate the voltage drop here, and then from here to here, and from here to here, I just calculate here, 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 and I sum up together and come back to the same point. At the same point, the voltage will be a constant. Means I sum this one, sum this one, sum this one, and to the end, 0, because I finish one loop. Okay? This is two equations due by Gier Hofu, I don't know how to spell it. You say it in English, Gier Hofu or whatever. Is the sum of current is 0 at the single point, and the sum of the voltage is 0 for a loop. Okay? So the first equation try to tell you is that if you look at the figure 28-4 on the leftmost, first there will be a, let me try to draw it. Current I. So first there is energy of epsilon, that's the voltage. The voltage sometimes we use V, sometimes we use epsilon because this is so-called EMF, electromotive force. Basically, it's a battery. The battery, the voltage generated from some chemical reaction. The chemical reaction to move ion from one side to the other side to form something like a capacitor. However, there will be some chemical to drag and move the ion inside the capacitor so that we draw it like a battery. Okay? So this thing first is a epsilon, and then the current goes through it. There is small r. We call it inner resistance. Let's see if is there a particular name for it? This is a resistor inside the battery. So the battery outside you look at the same block of battery. However, inside it have two components. One is provide voltage. One is a resistance in series of this battery. Okay. So when there is a current, it's I over small r. And on the other side, there is a load. The load is a resistor. For example, if it's a lamp or if something, so it's minus I times R is equal to 0. But each of them is the voltage. It's V1, V2, and V3. And the sum of them during the whole loop is equal to 0. That's this equation, okay? We say the voltage, you add up here, add up here, add up here, and you come back to here, the voltage will be the same. So delta V is equal to 0. So if you look at the figure part B, 28-4 part B, the voltage at VA, first it will be increased to a certain potential epsilon by the battery, and then due to the current goes through the inside series resistance R, small r, it's dropped by IR, and then the wire doesn't drop any in voltage, so it's the flat line, and then used by the capital R, the load resistor, and then IR to the 0, and then go back to VA. Okay? So that's the whole series part. Let's flip page. Let's look at the sample problem 28-1. What's the current inside the circuit? Okay, the circuit is quite complicated, too many things. However, the equation is really simple. It just the sum of the voltage is equal to 0 during the whole loop. Okay, so if let's say we go through here, we assume the current is go this way. So first it's 2.3 times I, and it will go up, right? The current will go this way. So I mean say this is 0, so this should be negative. Don't worry about this. They are the same thing. Depending on if I do it this way or do it that way. Let's assume let's do it this way. Okay. So the first thing is negative. It will go a little bit lower, and then the voltage will be sum up to 4.4. Go up. Same. Say the reverse the battery, so it will go negative. Okay. 1.8. It will keep going like this. The current will go through the resistor, so 1.8 times I. And then this one is 5.5 times I. Okay, this one is equal to 0. Means what? This one is 2.3 is equal to I times this one plus this one plus this one, 4.1, 9.6 ohm. So current is something, whatever it is, 240 milliamp. Okay, that's part A. How about part B? what's the potential difference between the terminals of battery 1? The battery is look like something have both of them, right? So it will be 4.4 watts minus 0.24, that's the current, times the resistance, which is 2.3 ohm. That will be the voltage, which is 3.8. This tells us what? In the normal battery, although we are telling it is 1.5 in watts, however, as soon as we put some load on it, it means that we draw some current through it, the voltage on the outside of the battery will start decrease. Okay, decrease a little bit. Fortunately, the inside resistance is not too big, so that the decrease of the voltage is not that big. It's still around 1.5. However, it will reduce. Do you know that the how to say the normal AA battery is 1.5 watts. The alkaline battery, how to say it? But the rechargeable lithium battery is 1.2 in watts, right? And you can interchange of them. In the same camera or same thing, you can change. Either use this battery or use that battery, although both of them have, although they have different voltage. But why is that? It's because this one, the inside the series resistance is much larger than this one. So when you draw the current, the outside circuit will not say 1.5, they will only say about 1.2 watts. Okay? So that's what's happening with this kind of thing. Okay, so that's page 641. Let's keep going. Okay, table 28-1, that's very important. Let's talk about different resistance and the capacitor. In series of resistance, it just sum up. If it's parallel, then it is 1 over R to the sum, and then 1 over R equal. Capacitor just reverse of resistance in terms of parallel or series. If in parallel, it's sum up, and then if it's in series, it's 1 over C to the sum. And if it's only two of them, multiply on the top and the sum on the bottom. That's the normal case, right? Okay, let's take a look at the sample 28-2. 28-2. What's the current through the battery? The current through battery is equal to what? V over R. So as long as we know the resistance, we know it, right? Okay, it's 20 ohm. These two are parallel to each other, right? Because this one and this one, so this one and this one, they are parallel to each other, 20 or 30. Equal to what? Okay, it doesn't solve for that way. So let me see. It's trouble. Okay, max. It will be the 20, 12, and 8 over the voltage. So currently is equal to the voltage 12 watts. The sum of them 20, 12 plus 8 is 40, right? So it's 0.3 amp. Okay, part B, what's the current through R2? What's the current through R2? R2 is here. Okay. Here we have something else. The total current is 0.3 amp. and then the current will be split between these two. What we have here is that I1 over I2 is equal to R2 over R1. Okay? If you do it the other way, it's I1 times R1 is equal to I2 times R2 equal to the voltage. This is two resistors in parallel to each other. So the current will be inverse proportional to the resistance. You can think about this way. They have same potential here and the same potential here. Means there's water flow on the top and on the bottom. And the one part is really smooth and the other part is really rough, all the bumpies. So what's happening is that the water is more like to fall off through the smooth part, go quicker, and on the bumpy part it will move slower and less amount of water to go through it. Okay, so the higher of the resistance, lower of the current. This one will be more proportional, so 0.3 over 5 times the small one is the larger part, so it's like this. Current will be 0.18. Okay, makes sense? And through R3, part C, just 0.3 minus 0.18 is 0.12. Okay, let's take a look on the next sample problem, 28-3. Think about that a little bit. This one you really need to use the voltage loop because there is too complicated. There are two loops. You cannot directly do a parallel or series resistance calculation. Okay, so how do you think about this? First, why can we not do the same parallel and the series calculation like last problem? Because it's too many batteries, and we don't know how to do a calculation of series of two batteries with some resistance. It's so hard. Okay, so means that we cannot consider these two are parallel to each other. It's simplified. So there will be a loop 1 and there will be a loop 2. Okay, we cannot get it into together. Second, there are many current. Okay, there are not just one of them. So there's, let's see, I1. I didn't do the definition as whatever is said in this book. I just do arbitrary things. S3. Okay. So what we found is that we have 3 definitions of current. The current goes through here, the current goes through here, and the current goes through here. So 3 unknowns. And let's see if we can get 3 equations. Of course, the first one is that I1 is equal to I2 plus I3. Sorry. Yeah. The current flow in will be equal to current flow out. Okay, that's the first one. Second one, let's look at this loop. This loop is a resistance of 2, and the internal current, let's say this is voltage equal to 0. Okay, doesn't matter where I put the voltage equal to 0, it's always back to the same part. So here the current will go I1 go this way. So it's 2 times I1 into negative. So the voltage will drop a little bit, and then will increase by 3 volts. And then will drop again by 2 times I1, and then drop once more by I3 this time. 4 times I3. And then drop again by this 6. What is equal to 0. Okay? What you say is only positive 3, negative 6 means some of the current, either I1 or I3, they will be negative. Means that the current either go this way or some current go this way. I don't care. I just solve it and it will tell me it's positive or negative. I'm looking at the second loop. Second loop is here, V is equal to 0. First, the voltage go up by 6. Then the voltage will be go up again because the current is go this way. So voltage is dropped from here to here. If I go the other way, it will go up. So 4 times I3. It will go through here. The voltage this time is dropped by 2 of I2. The voltage will drop by 6. The voltage will be dropped again by 2 of I2. And then it's back to the original point, is 0. Okay? So 3 equations, 3 unknowns. The 3 equations is 1, the current continuity, second, the loop, third, the loop. Okay? A lot of time, what's happening is that if you only have one loop, what you have is that inside of 3 unknowns, you only have 1 unknowns. And then you have 1 equation to solve for this equal to 0. Make sense? Okay, let me repeat. A lot of questions, you don't have the second arm. So you only have 1 loop with 1 unknown of I1. You don't have I2 and then I3 is equal to I1. So you have 1 unknown, 1 loop, 1 equation to solve for I1. That's normally what we did. But this case, we have 2 of them. So we have 3 unknowns and 3 equations. And you can solve it. The result is there on the textbook. I don't care. Any question for this one? Okay, if not, let's keep going. Page 648. That's the last section about RC circuit. Again, this one we talk about the voltage. The voltage is equal to I times R. On the other side is a charge of the voltage across the capacitor is Q over C equal to 0. Okay? However, the Q over C here by definition is I dq dt. The same I here, dq dt. So if you plug I there into it, what you have is something like R dq dt plus Q over C is ipso. Okay? By solving this equation, you get Q is equal to some constant 1 minus each potential minus T over RC. Okay? Don't worry about derivation. It's everything about derivative for the capacitor, the solving for the differential equation and the general solution. Okay? The thing I want you to remember is there is always a term called E minus T over RC. This is the term I want you to remember. It's always an exponential term that changes with a lifetime constant of RC. Okay? We call it tau is equal to R times C. Does it define here? Yeah, tau time constant 28-33 tau equal to RC. Okay, that's the time constant. And then on top of that, what you will have is that some constant. I don't know what constant is that. It can be either 1 minus E T over tau. Normally it's negative. There will be negative term, means that the exponential term is keep getting smaller, and at the end is go to 0. E to the minus infinity is equal to 0, right? Okay, so the exponential term will be die out at the end. So there's always a minus term, okay? Or sometimes it's something like say E minus T over tau. Okay? This curve is look like something like this, go to 0. And this curve is something look like this, go to a saturate. Okay? So it doesn't matter it's go to 0 or go to saturate. It's always changed by this E or E to the minus T over tau. And then you just need to analyze. At the beginning, it's a big number. At the end, it's small number. Or on the other side, at the beginning, it's small number. At the end, it's big number. Okay. So that's the solution for this part. Let's see if we have some. Okay, we don't have any example here. So any questions so far before I go through all the equations? Okay, then let's go over final equations. Can you get a summary? Do you have a summary equation from last time?
I don't even know why I'm going.
So the summary of the equations. And turn to chapter 26.
Summary of equation.
Have like the music thing.
It's scratch paper.
Wow.
Music thing. Oh,
Good.
brilliant.
The art exception, OG.
Do you have that? Or do you need to grab some? You have, okay. Page 26. Chapter 26. Let me try to get one more copy here. Just give me 1 minute.
You swear you
Wait, is it this one or this one or that
Oh,
one?
JK is wrong one.
JK Rowling.
Bless.
Oh my god, are you in the same class?
Huh?
Are you in the same class?
No.
What class are you in?
No, they are. Go around to the room.
You're in the RP or RC.
I'm taking
Okay,
a
we'll start first and we'll bring
Third
something
class.
to you. Okay?
Oh,
Nice.
very nice.
So,
You tried.
in chapter
That's all that
26,
matters.
what we talk about is that the charge equal to C times V. That's the first one. The
Wait.
that's from previous.
Wow. Oh dear.
这样，
Yeah.
Holy cow.
你还给我
没有都给他对吧？
给他，那我就没了吗？看见我是给过你的
A whole tree, Alex.
啊，
This is
It's like a quarter of a nickel.
Nickel mugger. The nickel mugger. You're the new nickel mugger.
The camera can't see him.
you have page 606.
你怎么后看呢？
Okay. Yeah. So when we talk about the capacitor, we are talking about the capacitor in Faraday, voltage in terms of the watt, and then Q is in terms of coolant. Okay, make sense? And then when we talk about capacitor, if it's a parallel plate, okay, the capital plate. This is chapter 26.
606.
Okay. The capacitor is equal to epsilon 0 times A over D. Proportional to the area, inverse proportional to the distance, space between two plates. And if we talk about the single sphere is equal to 4 pi epsilon times R. Okay?
Here we go.
In terms of capacitor, if we do this parallel, it will be sigma of C if it's parallel. And it will be 1 over sigma of 1 over Ci if it's in series. Oh, sorry. Yes, in series. Okay. The energy of the capacitor will be U equal to 1/2 CV squared, or analysis Q squared over 2C. But what we want to say is that the energy is really stored in the E field. Okay? The difference between this one and this one is this is the potential of the whole capacitor, the potential energy of the whole capacitor. This is the potential energy per volume in that E field. Okay? So that's a capacitor. Let's turn to page 27. So 27, the first thing is that we talk about the delta Q, is change of the current over the time. Sorry, the certain amount of current over a time density is the charge you put in. So current is in unit of ampere, second, and coulomb. So what we have for the resistance is that on one side, R times I is equal to V, and then the resistance is equal to rho times L over the area of A. Okay. If you want to know a little bit about the current density, the current density is look like this. The J is equal to J times area is current. I just write it down, okay, myself. And then the J is equal to sigma times E. Sigma is equal to 1 over rho. Okay? This part you don't need to really notice it. Next, talk about the power through the resistor. The power is equal to IV, or on the other side equal to I squared over times R, or V squared over R. Okay, both are okay. Okay, let's keep going to the circuit. That's chapter 28. Chapter 28. The first thing is that the sigma of VI over a loop is equal to 0. The sigma of the current at the single point P is equal to 0. That's the two equations we have. So there are power, current, the resistance. R is equal to sigma of Ri if it's in series. And 1 over R is equal to sigma 1 over Ri if we are in parallel. Okay, at the end, the last thing is talk about the RC constant. The RC constant, I just put it here, the tau is equal to R times C. And then the equation normally is look something like E minus T over tau. Okay? That's the normal changing exponential term. Okay, feel good? No?
Any questions, Jay?
Anyway,
And
let's
you start
start
from
the quiz.
Like jewel. You know what a jewel is? How do you spell jewel?
G.
What?
Okay, let's do the quiz.
In G?
Oh, it's different.
Oh, sorry, stable at wrong position.
Oh my god.
Bottom and
Try something new.
okay.
Oh my god, that's so
We don't have any.
It should be easy one, right? The circuit should be the most easy one compared all the other things. So let's try to do it quick.
oh my god. Generated.
What is there?
Try to focus on
Be
yours.
number one.
Okay. Yeah, just work on your own.
Really?
Try to do it quick. Whoever finish, let me know. You can stop at that moment. Try to do it quick. Quicker, someone already do the second page.
I'm slow. No!
Okay,
Hey, I did it.
That was 180.
No,
I just did it almost. Keep track of the
Oh, I
tip.
did it.
we're on air. Okay, can you get 2006?
I did it.
2006. Let's see which
I
one.
still can't do it. Like,
That's really unfortunate.
like, oh, like, dude, I can do
2006?
this. Yes, right.
Number 3.
I could just throw it up. What?
2006, number 3. So it's this one.
Why do you guys have the same?
Number 3.
So funny though.
Well, I bought mine cheaper than his, so they're smaller than mine.
Can
They're
you
on
guys
sale. They're the same case and stuff.
Mine were on sale.
My question is, why are we wearing it?
Try to solve yourself and let me know your answer.
Go.
Okay?
Can't find your stuff.
2006, number 3.
I think I lost 2006. I found 2003. Oh, there's.
There's RC circuit. Initial on charge. Switch is closed at t equal to 0. It's start to change. The second circuit, the resistance is double. Capacitor is half. Thank you. Resistance is doubled. And the capacitor is half. And think about the graph. What does it look like? Between A, B, and C, which one you think? E?
Wait, number 3?
3? Think about more.
D.
Think more.
Oh, must be. Wait, what?
Probably it's not B, C,
Then
or
it's C.
It's not C,
Wait, what is
I think.
You keep guessing.
Remember tau is RC?
So,
Tau is the same.
sure.
Just think yourself, don't discuss. Okay, let's look at together. So the resistance change, the resistance is doubled, and then the capacitor is halved.
Cool.
Okay, so first, the long time limit to the voltage change is 2 times Vm. Is that possible? No. The voltage Vm, right? So you cannot be more than that. B, let's skip. C, the voltage increase more slowly with longer time limit, but final voltage is the same. Okay, is longer slowly or not? What we know is that tau is equal to R times C, right? R is doubled, C is halved, so the tau doesn't change, which means the change will not be slow or quick. So C is not, as well as D. D is quicker, is not. Answer E, the long time limit of the voltage turned to half of the Vm. Is that true? If we think about the circuit, so there is a resistance and there is a capacitor, and then come back to the voltage. After it switch off, what's happening is that this one start charging. At the end, it's fully charged, right? When it's fully charged, the voltage here will be equal to the voltage here, since the current here is equal to 0. Make sense? So the voltage now to half of the Vm. Doesn't matter what the resistance here. It's always current equal to 0 and the voltage equal to 0. So the voltage is always here, right? Means E is not right. If look at B, the charge, no change are necessary. The new graph is identical to the original, which is true. Okay? How about number 4? Number 3 is plot voltage. Number 4 is plot current of the circuit. How about number 4?
You're right.
How do you know?
I think you're right.
Okay, how about number 4? Which one do you think? Let's look at the initial current. Okay, the current is equal to what? V over R, right? At initial, the capacitor, the voltage between capacitor is what? 0? The voltage here is V, right? So it's V minus 0. So R at beginning is R, at later is 2R, right? So the I prime will be half of the initial current. Make sense? That means answer A is not right. Answer B, initial current is the same, not right. Answer C, no net charge, no change are necessary, not right. D and E, how about these two? D? Yes, answer is D, because the tau. RC doesn't change, it's 2R times C over 2, so the tau will be the same. So the decay rate will be the same, okay? However, just the initial current. So what's happening is that the initial current like this go to 0, and then the new circuit is go this. The only thing changed is that the current initial will be reduced by half due to the resistance limiting the current. However, the decay rate means from here to 1/2 and from here to 1/2, they are at same amount of time. Okay? The exponential term, E minus T over tau, the tau will be the same, so T will be the same. Okay, let me pass out this one and then we can talk more. Okay. Number 1, number 2, I think. All the answers here, so check your answers. Number 1, number 2, I think there's some calculation. Do more calculation yourself. Let me see if there's one. Let's talk about number 10, okay? So after you comment, let's look at number 10.
That's cool. They're
I
not
had
more
the right
films.
answer, but
Oh, lava lamp.
I
Yeah,
had
of
the
course.
answer, but I wasted.
That's really unfortunate. Why did you erase it?
So for number 10, it says there are 4 same light. Okay? For number 10, there are 4 same light. And which bulb have the brightest? Brightest means the highest in current, right? So which one have higher in current? E, right? This one, and then you split 2 of them. Doesn't matter which one, how does they go, but the sum of this one is the maximum one. Okay, so it should be easy. Okay, I won't talk more about this. Let me know if you have questions in this set. Let's go back to 2006. We are on number 5 now. Okay, number 5. Number 5 is what? It's the battery with plug. Okay. Go quick. Any guess?
Is it A?
Brighten, let's assume it means brighter. Okay, think about it again. Or from dark to bright or brighter. So A is not right.
Stop guessing.
How come when I say something, you always call me
You
guessing?
said A and then you said B.
That was my second choice.
Okay, I'm assuming your third choice was C.
No, it's not. Well, yeah, it is. Then it's, I think it's like D. I mean E. Then
It's
D.
totally not guessing, bro.
Oh wait, hang on.
Let's think seriously. Do I have an answer?
It's just a
Okay. Let's think it seriously, okay, Joey? Let's do number 1. Let bubble 1 get brighter. Is that true or not? Let me ask the first question first. So this is a circuit. So what's happening is at time equal to 0, this switch closed. After t equal to 0, is there any current goes through this lamp or not? Let me ask my question again. After t equals 0, this switch closed. These 2 voltage, they are the same, right? Is there any current go through this or not? No?
Not yet.
Go through the calculation, right? So first, let's say V is equal to 0 here. Okay? So it's plus V. And then the current goes through this one, let's say IR. And then it will go through here, minus V. And it's go back to here, V is equal to 0, right? So means these two cancel each other, IR is equal to 0, means what? Current is 0. At t smaller than 0, there's no current because it's open circuit, right? At t equals to 0 when it's closed, because these 2 voltages are the same, so the current is still 0. Current 0 before, current 0 after. Does it change? Nothing change. How about this one? Nothing change, right? So if you look at its answer E, the current for the from the battery 1 is unchanged because the current from here is not changed. The current is still this one go to here. That's the only current is happen through this battery 1. Okay?
Is that like this?
Doesn't make a difference.
It does?
Okay, let's go to 2005. 2005, number 14.
It doesn't matter. Those who know the positive of connection is the composite thing. It simply matters.
Mm. 2005, number 14. And I need you to do it quicker, okay?
Go.
Be hurry.
I can't find the sheet. Find the picture.
Do it like in the physics competition. Do it quick. It's a constant current source. Means that doesn't matter what happens, the current is always the same.
Current device.
Oh.
Current device means that the current through this device is always the same. Doesn't matter what's happening outside.
Let's see.
Okay, yeah, that's correct. So let's look at it together. Argument A, bubble 1 become dimmer, is that true or not? No, because the current doesn't change, right? The same amount of current goes through it. And the power is what? I squared over times R, right? So that it doesn't change. Argument B, the power from the current device is increased. Okay? What's happening is that at t equal to 0, when this one connect, there's R1, R2, and R3. Sorry. R2 become to R2 prime, and R2 prime is in the parallel of R2 and R3. So this one is R2 plus R3, right? The total of this resistance come to here. And what we know is that when it's parallel, the final resistance will be smaller than R2 and will be smaller than R3. Will be smaller than both of them. Okay? So this one will be smaller. Means what? Means the total power is equal to I squared times R. R is have two parts, R1 plus R2 or plus R2 prime. And what we know is R2 prime is smaller than R2. So this one gets smaller and P gets smaller. Okay? So for argument B, the current device, the power is increased. It's not true because R2 prime is smaller than R2. Okay? C, let's skip. D, the bubble number 2 get brighter. Brighter means what? Power is V squared over R, right? R doesn't change. The voltage is get bigger or smaller. R2 and R3, they are parallel, get R2 prime. R2 prime is smaller than R2. So the voltage across here is smaller because R2 prime is decreased, right? So the voltage is smaller. When it's smaller, R2 doesn't change, so the power will get smaller. Make sense? So that's number D. It's not true. All three bubbles are equal bright. The power is equal to what? I squared times R. The current here is split to two of them, so the current is definitely different, right? So that the power. So what you saw is that when I talk about power, sometimes I want to use voltage, sometimes I use current, and sometimes I use P equal to I times V. Depending on which part I want to talk. For this one, I know the current will speak to two of them, so I want to make an argument from current. For this one, I know that the voltage here will drop, so I use voltage. Just depend on what I want to use, okay? Argument 3. C, the voltage between point C and D decrease, which is true, right? R2 prime is smaller. R2 is larger than R2 prime, so that the voltage across R2 prime will be reduced, decrease. Okay? Yeah. Let's keep going. Number 15, I believe. Yes, number 15. All the capacitors. B? Okay.
This one or this one?
Okay, let's look at it together.
Probably because this one
How to get this?
So the most important thing for this question is that how you simplify the circuit to tell which part and which part are in series and which part are in parallel. So what I want to tell you is some general thing you will use in the future, okay? So first thing is that from the bottom, so if there's a battery, you just put it 0, easy, right? Find the wire, follow the wire, it's 0, okay? 0, 0, okay? Anyway, you don't need to mention this two, but here is 0. From the positive part is energy of V, come to here is V, come to here is V, right? Look at all the joint. There's a joint, let's say it's a joint, okay? Everything is other than this, let's assume is Vx. Okay, I don't know what's that. Now I will hold this wire, I will shake it. Okay, say what's happened. So what's happened is that the first thing, from V to Vx, there will be a capacitor. Make sense? Okay. This one, from V to 0. 0 is a capacitor. Okay? This one is from Vx to 0. This one from Vx to 0. Okay, it's clear, right? These two are parallel to each other, and then in series of this and parallel to this. Parallel to this is 2C. 2C and C, 2 times 1 plus 2 plus 1, so this is 3 halves. I mean 2 thirds. See? In parallel of this, so it's 3/5 C. Okay? Answer should be answer B. Boy. Okay? Next one, let's get 2004. Everyone is ready? 2004, number 15. Okay, let's go. Number 15. 2004, number 15.
We already did that? Yeah. Wait, what? We already did 2004.
We did 2004, number 13.
Sure. Or 14 or 15? What? 15. We already did that. Yeah, we already did 15.
Oh, we did 15?
I think you did 21.
Oh, sorry. Let's go to 21.
No.
Sorry, 21.
Well, what is it?
2004, 21. Go, go, go. D? Okay, 30 seconds. Everyone else. So this one basically there's a 1000 ohm, and then there's another 1000 ohm with a voltage meter, which have 1000 ohm as well. Okay, so this is 500 in parallel compared to this. So the total 112 watts. 80 watts will be here, 40 watts will be here. Okay, so it's answer D. Okay, number 22. Number 22. E, no? For this question, you need to be quick and be accurate. You cannot make mistake. A? Yes. So 2004, number 22. What we have is that we have two resistors in series, right? Means what? Means current is the same. So if I want to calculate the power, what should I do? It's I squared times R, right? Current is the same, so it's only proportional to R. One is R, one is 4 times R. So the power will be 4 times as well. So it's number 8. Okay? 22 should be easy. Number 26. Number 26.
Okay. Good job.
Which resistor has greatest current go through it? Okay, it should be A, right? Yeah, because A is in the main path and then it's separated to 2 branches. So the current inside will be larger than the other. Okay, number 27. Which one have most potential difference across that resistor? Any guess?
See?
See? Okay, that's right. 30 seconds. Think about another way to do that.
Really?
For you, just think about another way to do it. There's multiple ways. Okay, so the first thing I want to think is that the voltage can be 1, 2, 3, 4, 5. What's the highest voltage in terms of 2, 3, 4, 5? Okay, I will pick the highest one and compare this one to this. Why I want to compare this? Because this one is self-complete, self-consistent system. If I assume here is 0 is V, the voltage here will be 5 over 3V, 5 over 2V. So definitely this is larger, right? So this one I don't care. Compare this two, this one is larger. This one is what? 9, 5V, right? Okay. Which one is larger? You multiply 27, 25, so this one is larger, right? I don't know how to do the comparison. For me, I can easily calculate this one is larger. Okay, next question. This one and this one, which one is larger? In this term, we need to really calculate everything, okay? So what we have is 5 ohm, 9 ohm. So multiply on the top, plus on the bottom, equal to 14 times 40, 45. This one is 3/5. So this is 9, 27 over 14. That's the part over here, okay? And the other part is 1. Which one is larger? This one is larger by almost double, okay? So this one is higher in resistance. Make sense for you? I do the sum, 9 and 5. I do the parallel by doing this. After this, I'm calculating how much really on that part. So it's plus 3 and this one compared to 1. Okay, that's number 27.
This one.
Okay, let's go to 2003.
Intelligent.
2003, number 20. 2003, number 20. Number 20. See? Okay. Okay. Can I share with you? So after it's closed, what's the potential difference at 15 ohm resistance? Okay, number C is right answer because 15 and 30 they are in parallel, right? So the voltage between them should difference between 15 and 30 should be exactly the same. It shouldn't be equal to the potential across 20 because one is 20 ohm, the 15 and the 30 in parallel to each other. This one, the resistance must be smaller than 15, right? Means that this one and this one, the voltage won't be the same. If the resistance here is equal to 20, then they are the same. However, when parallel two of them, the final result will be less than the small one. Okay? So A is not right. For BCD, basically we know it's equal, so it's answer C. Okay?
No.
Number 22. Number 22. Okay, number 22.
A.
Okay, number 22. What's
Two.
answer is A, right? 2 amp. Because one is 7 plus 2, so 9 ohm. The other is 4 plus 5, is 9 ohm. In parallel, so it's 9 over 2. And then the voltage is 9 volts, so divided by this one, I have 2 amp. Make sense? Okay. Number 23. What's the potential at point B respect to point D?
A.
See?
A.
Make sense? Should be super easy, right? So there's 9 volts. And then on the one arm is 7 and 2, and ask what's happening on here. So it's 2 volts here and 7 volts here. So it should be 2 volts. Answer is A, 23.
This takes up 7.
Okay, let's go to 2002.
Open 16.
What you saw is this is super easy, right? Number 14 of 2002. Give me answer.
What is that two?
It said after switch close, the current in the circuit reaches a constant value. Means it's stable.
C.
See? Okay. Okay, there are 3 branches. At the constant current, what's happening with this capacitor? Do you think it's fully charged or not fully charged? Fully charged. What's the voltage? The voltage will be exactly the same as the voltage of this battery, right? So if the same voltage, what's the current? 0, right? It's fully charged. I is equal to 0. So you don't need to worry about this. The current only goes through this resistor and this resistor. So 200, 400 multiply on the top, sum in the bottom. So that will be what? Ohm. And then divided by what kind of voltage? 10 watt. So it will be 3 over 40. So it's answer C. Okay. Number 16. Sorry, number 16 we have done it already or no?
No.
No?
We did 17.
Okay. E,
C.
C. How many resistance there? Resistor 4. The sum is what?
Oh.
20.
20.
You get 4 over 20.
Okay.
These
Okay.
So it's answer E, right? 4 over 20 is answer
Oh,
E.
I thought it was 10. Like, and I scribble over a lot of stuff.
Okay, that's number 16.
Just read it.
Number 28.
Wait, it says 6.
Excuse me. What?
there 28? Yes. It's 4 resistors, not 6.
Good job.
So no current goes to middle. What should be R3? No current goes through the ammeter means what?
Current going from R2 and then like to R4 is the same.
Yes. Or what? The voltage on the left and right of the ammeter should be the same. What's the voltage on the left and what's the voltage on the right?
D.
D, yeah. Think about another way to solve it.
Oh, sexy.
Okay, let's look at it together. So voltage here is 0, voltage here is V. Okay, I just assume that. The current here is 0, right? The resistance here is what? 0, right? Means the voltage between these two is 0, right? Okay, so V1 is equal to V2. V1 is equal to V2. Okay, second, this is current equal to 0, right? Means that if I don't have this branch, it's okay, totally. Makes sense? Okay, to calculate V1 here, 3 over R1 plus R3 times R3. This is what? V times R2 plus R4 times R4. Make sense? They should be equal to each other. And that means R3, R5, this is R1, R3, R4, R2 plus R4. I can cancel this one immediately, okay? Because if I flip it, R3, and on top is R1 plus R3, and then it's 1. I flip it, R4 in the bottom, R2, R4 is 1, so I can just cancel 1. Make sense? Okay, this one give us what? It's R3 equal to R1 times R4 over R2, which is answer D. That's number 28. Number 29. Number 29. Just simple calculation, right? Give me the answer. One thing talk about electron. One electron is how many coulomb?
1 over 6.2.
one electron is 1.6 times 10 to the negative 19 coulomb. So what's the answer? Okay, this one shouldn't be that hard, so let's just start. E, okay. Q equal to 3 times V, right? Okay, I want to ask wattage. Wattage equal to what? Q over C, right? Q is what? 1.5 times 10 to the 12 electrons. For each electron is 1.6 times 10 to the minus 19 coulombs. Over the C is what? 8.9 nanofarad. Nano means 10 to the minus 9. Okay, you put everything in, do the calculation, and result is 27 watt. Okay, so it's E. Okay, 2001. Got it?
Yeah.
Number 11. This one is interesting. Take a little bit of time. Let's talk about it. Number 11 of 2001. Okay, so let's do it together. This one is a little bit tricky. So it's talk about there is 500 watt of power, light bulb, right? So the power is about 500 watt. P is equal to what in terms of circuit? V times I, right? Okay, mechanically, the power is equal to what? F times L is equal to what? Work, right? If I divide by the time, then it's the power. Make sense? I need to divide by time here to this side. This is what? Power is equal to F times V. L over T is V, right? Velocity. Velocity is what? This is the talk about the rotation. Omega times R. Make sense? F times R is what? Is the torque they talk about, right? So it's tau times omega. Okay? So P is equal to this. Right now we can put everything in. In terms of ohmic, this is 350 radian per second. And then ask you about the tau, so it's 1.4. Okay, so answer is B. This is not a very typical electrical question, but however, it's asked about the power. Power have two parts. Normally we talk about voltage times current, which is the light 500 watt. But actually you don't need to worry about it. Okay? We didn't use 120 watts at all. In the other side, we talk about mechanical part. In terms of F times L is W, F times V is the power, V is omega R times F is the torque, and omega. So we put in omega, we have the torque. Okay, let's do the last one, number 13. Okay, I mean, anyway, let's do it. Maybe not that number 13. Let's do number 17. Let's do number 17. This one is interesting as well. Number 17.
What is that? It's like the needle moves in a picture.
Oh.
Number 17.
Scale deflection.
Okay, let's do it together. This is a little bit tricky, so answer is A. Okay, that's no problem. Yeah. So normally when we talk about ideal ampere meter, what we assume is that the inner resistance is really equal to 0. And then the current just goes through it and give you a reading. Okay? However, what happens is that normally the scale of the ampere meter is not large enough. Means that, for example, I just need, let's say 1 microamp, 10⁻⁶, to go through the ampere meter and it's working good enough. So what happens is that I put another resistance beside it so that I can get the majority of the current will go through this path. And then just 1 microamp here, the other current will go through here. Okay? So when it's talk about 10 milliamp with 100 ohm, I can calculate the difference here is about 1 watt. Make sense? And then this question asks, okay, instead of 10 milliamp, I want to give you 10 amp. So it means that 10 milliamp here, 9.99 amp will go through here, through another resistance, and give you 1 watt. So what the resistance should be? So it's 1 watt over 10 amp is 0.1 ohm. Okay, so it's answer A. This one tells you what? It tells you that it doesn't mean the resistance here, the ampere meter resistance here is really small. Actually, the here, if let's say this is 1, I even put it a little bit larger. Let's say 1 milliamp. Okay, means that the resistance here is actually 1 kilo ohm. Okay, the ideal ampere meter, if the scale is small, it doesn't mean the resistance, the series resistance is really small. It's quite big. However, when you want to put through more and more current goes through it, you will find that you need to in parallel with really small resistor, 0.1 amp. So the total resistance in this branch is much smaller than this. Okay, that's why we call the ampere meter, ideal ampere meter, the resistance is really small. It doesn't mean in the height it's really small. It means that in parallel with a really small resistor that bring the whole resistor much small. Make sense? Okay, we will stop here and we may do more electrical next time. Okay? Thank you for your attention. Oh, the homework you didn't turn in today, but turn in next time. 2006 is last time. 2005 is this time. To turn in two of them. The mechanical part, okay, not the electrical part. The mechanical part of 2006 and 2005. You just read the question. If you think you can solve it, solve it. Okay? Turn in next time.
Smart.